All right, in this video we're going to talk a little bit about collisions. So the first thing we're going to try to do is we're going to define what a collision is. So a collision is whenever you have an interaction between two or more objects where you have large forces exerted over short times. So if you think about the kinds of collisions that you're used to hearing about, car crashes and so forth, there are very, very large forces in that interaction, but they occur over very, very short time intervals compared to the motion itself. So we're going to talk a little bit about how we analyze those kinds of systems, but the idea being that we're going to bring to bear some of the principles that we've already talked about in class. So the first one is this idea of the momentum principle. So if we have one or more objects, we're going to talk about the momentum of a multi-particle system and how that relates to the external forces over the time interval of the interaction. And in this case, as I'm talking about large forces, what I should actually be saying here is these are large internal forces. They're forces that are internal to the system. And so we can neglect the forces that are external to the system in situations where we have collisions because the time interval is short, and these forces, these external forces, are very small compared to the internal interactions. And so we have a situation where we are going to conserve the momentum of the system. That is, the system's initial momentum is equal to its final momentum. Now, this is always true in a collision. It's always a useful model in a collision. And it's often the first starting point for thinking about how these two things interact. Now, one of the other principles that we've been using a lot is this idea of energy conservation. And what we've talked about in a multi-particle system is this idea that the change in energy of the system is related to all of the external works that are done and any exchange of thermal energy across a boundary. Now, in a similar argument to that we have for momentum change, that is that the external stuff, the external interactions are small compared to the internal stuff, we're going to neglect both the work done and the thermal energy changes as a result of exchanges with the surroundings over the course of the collision, over the course of that interaction. And so what we're going to say is that the system conserves its energy as a result of being able to neglect these more external bits. So I'm going to get rid of some of this because we're going to talk a little bit more about the kinds of interactions that we have, the kinds of collisions that we have, and what they actually look like in detail. So if we're suggesting that we have both momentum conservation, that is that the change in the system's momentum before and after the collision is 0, so there is no change, there is just the momentum that it has before and the momentum that it has after the collision are identical. And similarly, we're going to argue that we have energy conservation, which is that the energy of the system before and the energy of the system after the collision are the same. These are our two governing ideas for collisions. Now, this one is relatively straightforward, the idea of momentum conservation, because we can track the velocities of these objects before and after the collision. And it's very clear what that momentum looks like. The energy of the system, on the other hand, is a little bit trickier to deal with because the system can have a variety of energies. But the two that we're going to keep track of when we're talking about the system energy are the kinetic energy and any internal energy that the system has. Those are the two bits that we care about. So the kinetic energy here is going to be associated with the motion of these objects. The internal energy, on the other hand, is associated with any sort of deformation, vibrations, rotations, and so forth that occur as a result of the interactions. Now, it turns out that the internal energy and how it changes is a very useful cue for thinking about the types of interactions or the types of collisions that one can have. So in a situation where you have an elastic collision, so a collision that is elastic is one where there is no change in the internal energy. That is, the system conserves its kinetic energy. So instead of talking about the energy before and the energy after of the system in total being conserved, in fact, that energy conservation boils down to the kinetic energy of the system before and after are the same. Now, this is a very special type of collision. This is the kind of collisions that you have when you have very sort of firm billiard ball type collisions, or when you have the interactions of various subatomic particles, electrons and so forth. The other type of collision that we have is what's called an inelastic collision. And inelastic collisions, the change in the internal energy of the system is non-zero. That is, the system deforms in some way. There are some vibrations associated with that. And therefore, the kinetic energy of the system is not conserved. It actually changes. It gets smaller, typically. K system initial is greater than K final, because the energy, the kinetic energy, is transformed to internal energy associated with the deformation and so forth. So these are the two kinds of collisions that we're going to work with. But what I want you to really pay attention to are these two principles which govern how we understand the interactions that occur during a collision. We neglect all the external forces and the external works and so forth, and we end up with being able to just look at how the momentum is conserved and how the energy is conserved.